Good afternoon, everyone, or good morning, depending on where you are. Welcome to our webinar on navigating challenges associated with PCR technologies in a cannabis laboratory. I am Tracy Szerszen. Next slide. I'd like to again welcome you to our webinar today. I am the president of Perry Johnson Laboratory Accreditation, and today we're going to be doing a joint webinar with Patrick Bird on a discussion on the PCR technologies and its challenges. We're also going to talk a little bit briefly about 17025. As some of you might be aware, PJLA accredits quite a bit of cannabis laboratories, also food, pharmaceutical facilities as well. And the reason why we did this presentation today was because just our feedback from us as an accreditation body of some things that we've seen in the field and as well as challenges, and we asked Pat to provide some input from his expertise on what he's seen and potentially some ideas for laboratories to get past those challenges. And then we're going to have some time for questions and answers at the end of our call. Next slide. Just some webinar housekeeping for today. This webinar is being recorded. All webinars, including this one, is available on our website. This will be available shortly after the conclusion of the webinar today. We do have a YouTube channel. You could download the webinar on or past webinars, or again, go to our website under the past webinar section. As you've noticed, everyone is muted at this time and will be muted for the entire webinar. But we are encouraging everyone to please use your questions toolbar to enter any questions you may have in relation to this webinar, and we will get to those at the end. Next slide. So I want to talk about a little bit about 17025. If you were part of our last webinar we did on the update to AOAC, we touched upon the requirements in section 7.2, which is a lengthy section about the selection of methods. It also talks about validation of methods. So just to recap what 7.2 is stating for the requirements for 17025 for laboratories, is that laboratories need to ensure that whatever method they're selecting, that it's appropriate for that test. And that methods shall be up to date and available to personnel. And where available, laboratories should use national or international methods that are reputable and ensure that your personnel has the latest version of those methods. So when we talk about this topic today, particularly in the cannabis industry, the PCR technology has been introduced as an alternative to the plating criteria or plating methods. So with that, there's still a lack of methods being validated in the industry. I guess not validated, but validated or nationally known accepted methods for certain things. And with that, as an accreditation body, we accept laboratories to develop their own in-house methods. And in this particular area is one that's been brought on to the cannabis industry, which is great because we understand that it might be a quicker tool, a quicker method to use to do your micro testing. But there are things that we expect as an accreditation body from the laboratories. So here just goes over what the 17025 standard says in regard to method validation. So I'm not going to read them all, but A through F of 722, I believe, talks about method validation and all these things that need to occur when you're validating your own in-house methods. So some of those things that it needs to be a planned activity. You need to train personnel, and then you don't need to create the method once, but you also have to re-verify it periodically to make sure, again, going up to bullet point 1, that it's fit for the use of the test. So there's all these things that we will expect when laboratories develop their own in-house methods, regardless if laboratory A has purchased a technique from, particularly in the cannabis industry, from a particular manufacturer. You still have to take that responsibility, and you have to know what these systems do. You have to be educated, and you have to demonstrate that to us. Next slide. So continuing on, 7224 of the validation of methods criteria and 17025 does ask for specific things in regard to validation. And here they're listed. This comes right out of 17025. So, again, having a validation procedure, the specification of those requirements, determining the performance characteristics, understanding the results obtained, and a statement of the validity of the method. So it is a lot of work that goes into validating your methods. Next slide. So just our expectation is, one, we want you to meet the 17025 requirements in regard to method validation. There's multiple ways you can validate a method. There's available resources that you could obtain from different industry groups, or potentially start with a method that's already been in place for several years, potentially in the food, maybe environmental industry, and utilize that as a baseline. But again, we expect you to follow 17025, and then when it comes to this type of in-house method development or assessment, during the assessment, we're going to assess your competency in regard to the development of that method. How did you follow 17025? And then we're going to look to see how you're performing that. So we want to make sure it's clear to everyone that during an assessment, when you're creating in-house methods, is that you need to have this data available. We need to have the discussion. We need to make sure that we feel confident that your method has been developed appropriately and it is fit for the use of the test you're performing. And you, as a laboratory, obviously would want that as well. There's a lot of risk that's involved with in-house development, and ensuring that you're doing it as accurately as possible is really important, particularly in this industry. And we, as the accreditor in the cannabis industry, we're not the only ones looking at your data. So many states require data packages to be provided as part of their review. So you want to ensure you're following 17025 and provide them the same confidence that you would provide to us during an on-site assessment. Okay, so with that, I just wanted to touch upon why we decided to talk about this particular technique. Again, it's been one of our challenges with some of the laboratories trying to understand what goes into this method validation process for this. And this is a trickier technique that some laboratories might have some difficulty getting in place right away because they're used to the standard plating techniques. But I think that what's important is that I think the states have particularly understood that this is something that's going to be used, or they're seeing it being used. So it's going to be something that I think we'll start seeing across the board, for many of the cannabis laboratories, particularly, starting to use, as it again expedites their test. Again, we just want to make sure that you clearly understand how this all works. So with that, I'd like to introduce Pat Bird again. So Pat, thank you for coming back for another webinar. Pat's from PMB BioTek Consulting. He works with method developers, contract laboratories in the industry to identify solutions to emerging microbiological issues, optimizing method workflows, and designing validation studies. Pat, as an active member of AOAC CASP, previously serving as a co-chair of Microbiology Contaminants Working Group and as a co-convener for several projects with the Food Micro Method Validation Working Group 3. Pat holds a Bachelor of Science in Microbiology from Ohio State and Master's in Food Safety from Michigan State. So I'd like to go ahead and welcome Pat and let him now take over and provide his presentation on our challenges on using molecular methods. Thank you, Pat.
Thank you, Tracy, and I appreciate you for inviting me back again today to speak on this topic. And as you mentioned, we're going to talk today about how accurate is the method you're using, and we're going to focus on molecular technologies and PCR in general for this presentation. I'm hoping that as we discuss these technologies, I should say, we'll have a better understanding of where their strengths and limitations are, And ultimately, the participants today are going to come out with a better understanding of how they can essentially work around what we have deemed spurious signals. And that is a term that we use to sometimes talk about invalid or indeterminate type of results. So the presentation is going to do just a brief overview of microbiology testing. So I want everyone to have the same background. So we're going to talk a little bit about the different technologies that are out there. This will be a focus on technologies in general, or methodologies in general, not specific methods by technology providers. Then we're going to talk about, what are these companies doing to essentially reduce invalid results when we're testing products. And a lot of this work has been started in the food industry and is now being transitioned into the cannabis industry. And there's some actual real world examples that I have from working with labs that have used certain techniques to eliminate these spurious signals. And then, very briefly at the end, I just want to bring to everyone's attention, just some non-molecular technologies that people, may start thinking about using in their facilities. So whether they're either non-traditional or they potentially could offer some advantages, and I'll speak to why there could be some advantages to them. So I always like to start with the original history of microbiology, and what have we done for the last 100 years? And essentially, you can see when you look at this timeline, culture-based methods have been around for a long time, and they really weren't replaced as the dominant methods until the 60s or 70s, and that's more for the food industry. We still see culture-based methods used in the food industry, although they've kind of gone by the wayward side. What's interesting is that there are certain states are requiring more culture-based methods for cannabis. So we're retraining labs and microbiologists on these techniques because universities have moved beyond the initial basic training skills that we use for these and moved to more high-end and rapid detection. After culture-based methods, we moved to essentially immunoassays, so antibody antigen interactions, and then we moved into the PCR age in the mid 80s, although it really didn't become commercialized until the late 90s, early aughts. We also started to see the introduction of chromogens, whether that was into ELISA immunoassay technologies or culture media. And then recently we've kind of moved into what we call the omnics age. And we're starting to see sequencing, although sequencing is used rarely in the cannabis industry. It's used more for outbreak tracing. But other types of technology, more so coming from the analytical chemistry realm, because laboratories have these technologies, so can they repurpose them from micro and use the same technology to get the same result? So culture-based methods, these are pretty simple. We have, whether it's either quantitative, which is our left-hand side, or qualitative on the right-hand side. You have a basic sample prep where you're homogenizing a sample in either an enrichment broth or a dilution buffer. For quantitative, we dilute out the product as needed to be able to enumerate colonies onto selective or non-selective plates. So this can be used for anything from total counts to specific organism tests such as E. coli or coliform. And then for pathogenic testing, we are using enrichment broth with whether it's primary and then followed by a selective secondary, or adding selective supplements to it to isolate our target organisms, and then we use some sort of cultural confirmation to further isolate colonies at present. And the idea behind this is, we are trying to optimize the growth of these organisms from that exponential phase to this saturation phase so that we can recover them on culture media. Culture-based methods, for the most part, are relatively cheap to run. And if you're trained properly, they're easy to perform, but they're labor intensive. So there's a lot of steps that often have to be employed, and they take long. And most micro labs in a cannabis industry are not set up to do culture-based methods because of the requirements for different incubator temperatures and the incubation times that are required, or some of the equipment that is needed for this type of testing. So they're not often utilized. And some other issues with them is just how do you discern what is your target from your non-target? So you have a traditional salmonella organism growing on a culture plate, and then another plate that looks completely different, but that is still salmonella. That's just an atypical salmonella that's present. And then lastly, you also have another organism that potentially could look like that middle plate, but this is a non-target. So you have a salmonella that's traditional, non-traditional, and then this last one's actually a Klebsiella. So being able to, if you don't have traditional looking colonies or typical looking colonies, do you have the staff that can isolate or determine that? And then you start talking about traditional plate counting methods, and you can get plates like this where you have a whole host of a mess on that plate, and enumerating what's fungal growth and what's bacterial growth can be quite cumbersome, and in this case, virtually impossible. So that's why, as a consultant and, working with technology providers in the government, we tried to move away from culture-based techniques. And briefly, as I said, after the culture-based techniques, we came into the ELISAs where we started to see antibody antigen reactions, and there's multiple different types of ELISAs. Some of the benefits for it was we had your quicker turnaround time, and the sensitivity was at least the same as culture-based methods. The workflow is pretty easy, and if you automate it, it can be quite smooth. But while they traditionally have not been as sensitive as molecular-based methods, we have seen an increased sensitivity and selectivity with these technologies as they move to monoclonal type antibodies. And then, came PCR, and the idea behind taking bacterial DNA or fungal DNA and, splitting it, making copies of it, and then repeating that process over and over again, but tagging those copies so that it starts to fluoresce at a certain concentration, allowed us to really rapidly detect whether an organism was present in a sample. And so that's the basics of your, most of your PCR methods. We take small amounts of DNA and we rapidly increase those concentrations with marked fluorescent markers to detect using, optics. And in general, PCR is a pretty robust method, although it does have some tendencies where you can have inhibition based on compounds of the sample that you're evaluating. So while we view PCR, I think, from a micro community as the gold standard, there are still limitations, and that's why we're here today, because we're going to discuss that. Now, similar to PCR, and I want to mention this, so when I like to talk about limitations of molecular or PCR, it really often applies to molecular methods in general. So we have really two different categories of molecular methods that we'll talk about that are rapid detection. You have PCR, where we saw that amplification on the previous slide, and that amplification is done at multiple temperatures. So what you have is a cycle where we allow the DNA to anneal at a lower temperature, and then the denaturing process takes place at a higher temperature. Conversely, when we talk about isothermal amplification, what we're using is proprietary, enzymes that will either, nick, which is, used in near technology, or, essentially cleave the DNA in certain instances so that we can perform our amplification at a single temperature. So whereas PCR is this really powerful technique, when we start to talk about isothermal amplification, it's all done at a single temperature. So it's even more rapid, can be even more rapid than PCR. Some near technologies can be run in as little as 20 minutes, and we can see enough amplification to detect organisms. They do have their limitations as well, though. Multiplexing with isothermal amplifications is much more difficult to do. So these traditionally tend to be a single plex PCR reaction. Building on PCR, more so PCR than isothermal, we have some microarray technologies, and this is commonly used in the cannabis industry. One of the largest diagnostic manufacturers in the cannabis industry has a microarray technology. And the idea behind it is you're doing the same process as PCR in essence, where you're increasing your DNA present in your sample. And that can either be done through a PCR process or sample enrichment to just get the organism growth up there. And then what you do is you take that target, let's say PCR in this case, the DNA, and you label it with probes and hybridize it to a specific microchip. And then you get a bioluminescence reaction, and that's how you can tell whether an organism is present or not. So microarray technologies are pretty cool because they're really inexpensive to run because of all the multiplex technologies. You can microarray 12, 15, 18 different targets if needed on a single chip in a single reaction area. They're highly sensitive and highly specific because it's the same process that we're looking for in PCR, where we have a known set of DNA primers that we're looking for. You can sometimes see cross-reactivity as we try to multiplex these out, and the actual hands-on time for these tends to be a little bit more in depth, although some automation can reduce that. Interestingly enough, a couple of the technologies that the food industry is starting to adopt that I could see ultimately move towards the cannabis industry is multitop detection because of the presence of mass specs at cannabis facilities, or IR spectroscopy. And so both of these are chemistry technologies, and they're being adopted in the micro industry to essentially ID organisms or detect organisms in a more rapid manner. So multitop right now is a validated technique to ID pathogenic organisms from agar plates, and they're looking to start to transition that into more complex matrix samples for rapid detection. The IR detection platform is really interesting. So we're not actually looking at specific organisms in this case, but if you're working with a facility that has fungal contamination, IR spec can start to provide information whether it's something that's reoccurring and it's the same organism that's there, or if it's a new organism that's coming into your facility and you're having contamination from an external source. And then lastly, ultimately, I think next generation sequencing will be the techniques that every microlab uses within a decade. We're not there yet from a cost standpoint because of the throughput to run the bioinformatics portion of this takes 6 to 8 hours after molecular processing. So you're looking at adding an extra day. But ultimately, the information that you can learn, whether it's the biomarkers present in a sample, again, whether it could be a persistent organism to your facility, or whether it's some coming from an external source, whether there's antibiotic resistant markers in there or other virulence markers. As we start to learn more about Aspergillus, are we going to find out that there's certain markers that need to be present to really make people sick? So maybe the regulations change and we don't need to test for Aspergillus in general, but we test for certain biomarkers that could be present that could produce mycotoxins or make immunocompromised people ill. Ultimately, I think that's where we could see NGS taking a role. So why do we love molecular methods in general? Well, one, time to result. We're looking at 18 to 24 hours of enrichment for bacterial methods. Some fungal methods have gotten down to 24 hours, but most are in the 40 to 48 hour range. But it's pretty rapid turnaround compared to anywhere from 5 to 7 days that are needed for cultural methods. Sensitivity, when we're talking about Salmonella, there's wide diversity. As I showed you those organisms earlier on the agar plates, that doesn't impact PCR. If Salmonella is there, they have targeted gene sequences, whether it's typical or atypical morphology on a plate, it will detect them, and it discriminates them from that Klebsiella. So you reduce some of that ambiguity that your technicians could have when reading a plate. The multiplex capability, I think, is the number one, and Aspergillus is the greatest example of this. Having a mycologist on staff or having an individual that can look at agar plates and really tell you which of the four, main target species of Aspergillus that is not something most labs will do. They'll run PCR, maybe a multiplex or a singleplex and then a multiplex, do a repeat analysis if they have a positive hit, and then they're comfortable moving forward with that. So you don't have to have that all those classifications when you're looking at something under a microscope. High capacity, you can run usually about 90 samples every 2 to 4 hours, depending on the method you're running. So it's pretty quick to do that, and you can store DNA lysates for long periods of time without it impacting the sample. So if you're limited on your throughput in your instrument, you still have the ability to extract samples and then just put them on the instrument as soon as you're done. And to be honest, most regulators are accepting PCR as the gold method. I say most because some states are saying they want to see plating data either alongside molecular or in lieu of molecular, but we're trying to convince them of switching that from an AOC standpoint. So what's the downside to molecular methods? Well, one is cost. A thermocycler isn't that expensive in general when you compare it to analytical chemistry instrument, but having a biological safety cabinet or a hood to perform the molecular work in, the various pipetters, heat blocks, those sorts of things, and the assays themselves can be expensive at times, especially the multiplex. The technical skills that you need to run the methods can sometimes require more than just a high school degree. So a lot of times the micro lab is the afterthought within the operations build out of a cannabis lab, and identifying individuals that have previous experience, whether it's in the food, clinical, or other cannabis labs, is key. And then lastly, and why we're here today, spurious signals. Getting results that are inhibited or invalid and being able to work around them, as well as, what happens when you get a positive result? If you retest it and it's negative, is it really a negative sample? If you took from a different portion of that batch, was the first one really a false positive? Or was it really a positive and then you just tested a different part of the plant that didn't have that target in it? So how do you eliminate those sorts of things? Well, really the first thing that companies are looking at is enrichment media. So when we talk about this, your general medias, your tryptic soy broths, your buffered peptone waters, they're specially designed to grow everything. So companies need to be able to either develop targeted enrichment media, whether it's for like STEC, pathogenic E. coli, Listeria, that will eliminate the background organisms that are in there, or they'll have specific supplements that they can add to the media that will help either, in this case, the Solus 1 supplement here, that is designed to reduce natural inhibitors from spice products. So this is something that the cannabis industry is going to be seeing in the next 6 months, because it's reduced the enrichment ratio 100-fold for certain spices, which have been a major issue for the FDA going on a decade now. So to test something like cinnamon for Salmonella, a facility has to do a 1 to 10,000 dilution of that sample. So that's 1 gram, into, a significant amount of media. It's up to like a liter. Well, the cost to do that is very expensive. So this supplement can bring it down to 1 gram into say 100 milliliters or 10 milliliters. So companies are starting to invest in these sorts of techniques. You'll also see specific supplements that are designed to target non-target organisms. So if you're looking for salmonella, we can then put phage or some other sort of supplement into the product that will reduce Klebsiella or Pseudomonas, which are going to be found on your flour product. And if they're not there, it will help us grow the salmonella to higher levels. You'll also see certain supplements such as like charcoal that can be added to products, and charcoal is a natural absorbent, and it pulls out PCR inhibitors from supplements. So if you're looking for a way to validate an in-house method, I always suggest looking at charcoal first. Adding some charcoal to your enrichment protocol can really help reduce some of that background interference you see. And it doesn't have to be at a high concentration, and charcoal is a relatively cheap product to use. All right, so thinking beyond the enrichment protocol, what we want to recommend to labs is start to view the extraction processes you're using. So can you automate it? When you start to automate extraction processes, not only do you save time from a labor standpoint and an efficiency standpoint, but they're more uniform. So you're going to reduce transferring particulate from one sample to the next. You're going to have more uniform reaction volumes in all of your samples. You eliminate that human error from it. There is more capital investment that's required up front, but it's minimal when it's compared to a chemistry capital equipment investment. I think immunomagnetic separation. So this one is already being employed in the industry, but we'll start to see other companies bring their kind of techniques into it. So whether it's a traditional IMS in a tube, where you're using paramagnetic beads to say pull your target bacteria or your target DNA away, and then be able to eliminate all of your inhibitors from that sample, or whether you want to use something such as the PIC pen, which is it's a micropipetter that performs the IMS in a deep well plate and using the pen, which has magnets on it. So this device is pretty slick, and it's been highly adopted by the meat industry to target STEC from non-pathogenic E. coli. E. coli is present in a lot of meat, so they can eliminate a lot of that general E. coli by using the PIC pen process. And it's the same thought process we're looking at when we talk about flour and all of that contamination that's in there. If you're looking for Aspergillus, you can get rid of the other mold species in there and just keep your targeted organisms present using these IMS procedures. And IMS stands for immunomagnetic separation. So in addition to using automated extraction or IMS, you can invest in different filtration techniques to remove those inhibitors before you go to PCR. That's the idea, is that we want to try and eliminate some of these before we actually take it to the molecular method. So whether you're using like a silica-based column where you're only allowing the target bacteria to get through because you can spin it and separate it, and so only fine, very small organisms will actually get through, and the particulate is bound up in that silica. And so there's a whole host of different methods that you can use. And these prep-seeks and these extraction protocols are universal. So it's something that you can explore in your lab to really optimize a technology you're already using to reduce those false positive results or those invalid results you may be seeing. A lot of these method developers don't have the ability to get cannabis that has high levels of THC on site at their facility. And because if they bring hemp into their facility to do some R&D work with it, and it ends up being tested and having high concentrations of THC, they can have legal ramifications for that. So they don't bring any of this product in. So they're really looking to laboratories to do some of this additional R&D work within their internal method validations. So another technique that the companies are using is essentially improved lysis or purification reagents. And so what do we mean by this? So there are certain digestion buffers that companies such as Invisible Sentinel or this Exo-Zapit reagent, that they're part of the lysis process. So rather than just a traditional lysis buffer where then you would heat it, and a combination of general, lysis chemicals and heat will cause your cells to lyse and you'll have your DNA present, but you're also going to have a lot of other, endogenous material in there. And so by improving on these lysis and purification reagents, and sorry, the one purification reagent from Biorad is also something that can be used. They essentially bind to inhibitory reagents in from the matrix and allow a cleaner sample to come out for that PCR analysis. So the Biorad reagent right now is being used in low moisture products that have high background counts. It hasn't been incorporated yet into their cannabis workflow unless you have false positive results. So they have studied it to some extent, but it's one of those where you could look to implement that early on. The Invisible Sentinel one, which is owned by bioMérieux, is already incorporated into their Aspergillus program. And the Exo-Zapit is really, it's just a company selling this Llysis that you could use to optimize your own molecular method. So the last thing that people are using are these DNA removal solutions. Oh, sorry, I'm eliminated one graphic there. There's actually two different types. So you can use a light-based, so this PMA process, where you will actually add a chemical to your sample. It's going to this is before you lyse, you're going to degrade any extracellular DNA that's present. So if the organism was there, but it's dead and it's no longer viable, you can reduce it by adding these chemical reagents and then mixing it with this PMA and light process, and it will degrade that. So after you do your lysis, you only have DNA from viable organisms. And other companies, Medicinal Genomics with their Grim Reaper, Biorad with their free DNA removal solution, bioMérieux with their PMAX solution are just a couple. Also have what we call essentially free DNA removal solutions, environmental DNA removal. So prior to lysis, you eliminate any extracellular DNA that's present. That's going to eliminate false positive results because what you're doing is you're just degrading it. And then you optimize your lysis reaction, and then you're only detecting DNA that was still present in viable organisms. The one thing with the DNA removal solutions, though, is that you really do have to clean up those chemicals prior to running your lysis. We have seen a 10-fold CT reduction in your PCR results. So if you had viable organisms there at 30 CTs, which is a strong, moderately strong positive sample, and you don't clean up your DNA removal solutions, it could be as low as 40 CT values, which often is called negative in samples. So it really does have to be something that you evaluate and make sure you run that protocol accurately. And they're not viable for all methods. So these types of techniques usually aren't employed in quantification PCR. So when you have methods that are for like total aerobic count, total yeast and mold, total coliform, you shouldn't be running an environmental DNA removal solution. You should be looking at maybe one of the other techniques we discussed to really eliminate background. These should be more for presence-absence tests. And I know we've got about 5 more minutes before we want to open this up for some Q&A. So I just want to talk a little bit, just a couple slides about some other types of technologies that you guys may start to see. So colorimetric-based methods essentially have been around for 50, 60, 70 years. But what we're seeing is a refocus on them using really targeted nanoparticles. So similar to PCR, we're having these particles are being designed where they're very specific for the target analyte. So you don't have to worry about, inhibited samples because they're binding to the organisms. There's not those PCR inhibitors that cause, issues with your fluorescence. They don't cause issues when we're looking at some of these colorimetric methods that they've designed these so that they move beyond them. You can still get it on darkly colored matrices, but that's usually talking about something like an infused chocolate product. So you do have to be wary of that. And most of these, though, have right now, from a validation standpoint, they're relatively limited to environmental surfaces or a very select number of matrices. So we're probably a couple years away from the nanoparticle community really getting into the cannabis industry. I think bacteriophage is going to be something that we start to see more common. So I mentioned earlier, this can already be employed from a supplement standpoint. So there are technologies out there, there are companies out there that sell bacteriophage that will target non-target organisms. So if you're looking for salmonella or you're looking for pathogenic E. coli, you can use bacteriophage to target their competitors and really reduce it. But we can also put bacteriophage in the product that will target the organisms we're looking for. And why would we want to do that? Well, think of this it's like a virus. So if you have salmonella in there and you have to grow it up, well, after 18 hours in a complex matrix, one cell of salmonella may reach, let's just say, 1,000 CFUs in the matrix. That may or may not be enough for your molecular method to detect it. If we put bacteriophage in there, and they infect those 3,000 cells, well, during that incubation phase where the bacteriophage is in there, that 3,000 can become 3 million pretty quickly because it's a nth degree replication. They infect the cell and then they multiply rapidly in the cell before they burst. So one phage may produce 100 new phages with each cell they infect. So we're able to rapidly increase it. You tend to sometimes see with these a little bit cross-reactivity, so that is the downside to bacteriophage. Microfluidics is an interesting concept in the sense that it's a relatively inexpensive method to use. And essentially you're taking a known cell or a known solution of a product, you're moving it through a narrow channel. And what you're doing is by narrowing the channel and passing it through, you can detect specific organisms. You can either enumerate them based on how they flow through the channel, or you can detect them based on their size or some sort of fluorescent marker that you could attach to it. We've also seen magnets and magnetic particles added to these to really enhance the detection or quantitation stage. And where they're really neat is that there's not a lot of capital equipment. This can be done on biochips. They can be done in very small, portable, handheld devices. So this is something that you could, in theory, take to your grow facility, and you could do testing on site there, or you could do potentially same-day testing on samples, because the detection can be very low with these. We do tend to see some matrix interference issues, so that's the biggest hurdle that these companies are having to overcome. And then the last two technologies briefly are just kind of enhancements to PCR, and that's why I wanted to bring them to your attention. So when we talk about droplet digital PCR, I think the best way to describe this is looking at the tubes at the bottom left-hand side of the picture. When you have a PCR measurement, you're just looking at the total fluorescence in that sample, over time. A digital PCR, you're actually looking at all of these individual droplets individualized. So you can actually quantify more accurately using PCR than you can using traditional PCR. So this type of technology could really be a game changer when we start to talk about, I want to do total yeast and mold, total coliform on my qPCR, and I want it to be extremely accurate. Digital droplet PCR is the way that kind of occurs. Now, unfortunately, this is a patented process right now, so only one company is really exploring it. So we have to wait a little bit before this becomes more popular in the cannabis industry. And then, RNA or reverse transcriptase PCR, these are more for, they've been employed in viral methods, but we're starting to see them employed in bacterial methods. And why they're important is because by using reverse transcriptase PCR, we're looking for RNA, which means the cell is still viable or from viable cells. So we're taking that RNA, we're building off of it, and then we're reversing it to DNA. So it just adds a little bit more steps to the process than traditional PCR, but it does ensure that you're getting viable organisms tested or present. So if you're worrying about false positive reactions, more so than invalid reactions, then RT-PCR could be a solution. Again, this kind of, to me, is like sequencing, where this and the droplet digital PCR are probably 5 years away from really being employed by cannabis labs. So that's the end of my presentation. You can see our contact information here, and I'm gonna open it up. I believe Tracy has some questions. And if you, again, want to ask questions, there is a question box that you can submit questions for us. So Tracy.
Thank you, Pat. That was a really good presentation, very informative. I'm going to just take a quick look here for some questions. If you just give me a second. Okay. Are you aware of any proficiency tests that are available for this?
When you mean proficiency tests, so right now there are a couple organizations that are preparing hemp samples is really what we have, and I think Emerald Scientific is the largest group that is selling them. So their technologies can be, or their samples can be used with molecular methods or any of these methods to do PT samples. AOAC is partnering with the National Institute of Standards and Technology, NIST, to create PT samples, a wider range of PT samples, but they're focusing right now on the chemistry aspect of it more so than the microbiology. I also believe USP is investigating producing hemp PT samples as well, but I'm not sure if they're available on the market just yet.
Okay, and then what are some recommendations? I know you went through a lot, but recommendations if a lab is going from the typical plating to this technique. So for them, some things for them to look out for. I know you went through some of the challenges, but just in summary, just some overall observations.
So what we have found is that if you want to run a simplified method, so the extraction protocol is minimalized, there needs to be some sort of dilution of your sample prior to analysis. So whether that is taking the primary enrichment and diluting it in some sort of type of neutralizing buffer, maximum recovery diluent, like a lethine broth, which is used to neutralize quat-based organisms or something to that extent, that is going to be key. Some of the techniques that I mentioned, like you can get purification reagents, those sorts of things. But if it's a simplified extraction protocol where it's just being heated with Llysis, there needs to be some sort of dilution process before then. If you're looking at a method that has maybe a little bit more in-depth extraction protocol and they're using magnetic beads as part of it, or there's multiple kind of extraction steps, from that standpoint, it's really investing more in the labor you're using to run the method. Those types of methods tend to have 30 to 40 steps versus 5 to 10 for a simplified method. So each one of those steps is a potential issue for error. So having an analyst that is skilled enough to work with very small volumes and understands where the pitfalls of those technologies can come about would be where I would say to troubleshoot there. And I know that's a very diverse things to look at. It really depends on the technology you want to adopt.
Okay. We got a question. How can you verify sensitivity of PCR method and also quantitative accuracy?
So, verifying essentially the sensitivity of the method would be trying to do some sort of verification test at a low level. When I work with labs, I usually recommend general verification guidance is spiking something around 30 CFUs to 50 CFUs, for a qualitative detection. So if you are looking at Salmonella, Stec, maybe Listeria in certain instances where presence absence result is required, you want to take your sample, homogenize it in the enrichment buffer you're going to test, and then spike it at a level that's reasonably low. If you go much lower than 30, you're going to have issues probably getting recovery. And in reality, you're not going to see while these methods often have a 1 or 2 CFU limit of detection, you're often not going to see organisms at that level. So a verification of the sensitivity at a higher level is acceptable. And that's recommended by ISO and the FDA for food testing. When we talk about quantitation, right now I am not a strong proponent of quantifying using molecular methods. We need to see more data to see them to be accurate. And I say that because we have had some issues with methods going through validation where they're trying to quantify. So I recommend that if you love your molecular technology and you want to quantify using it, try exploring testing it at a threshold instead. So what do I mean by that is that you would take your initial sample, if you're looking at, say, total aerobic count, homogenize it in a general diluent, and then dilute it to whatever the action thresholds are of your state. So if you have a 10,000 CFU per gram as the action limit for total aerobic count, you take your sample and you dilute it down to a 1 to 10,000 dilution, and then run it as a presence absence test on your molecular method. If it comes up as a positive result, you're greater than 10,000 CFUs per gram in that sample. If it's negative, you're less than 10,000. I think that's the most accurate way right now to run molecular methods until we have refined the techniques a little bit more closely. The diversity of organisms when we're talking about total aerobic count, total yeast and mold count, even total coliform to an extent, is pretty extensive. And so for a method to be as accurate as it needs to be for those action limits, having more of a threshold detection is my recommendation.
Okay, let me see if we have any more. Okay, so that looks like that was the extent of our questions today. If anyone has any questions that come to mind after this webinar, you have our contact information here. Feel free to email us. And I thank you all very much, and please continue to sign up for our free webinars. We do have one every month. I know we have one coming up in July as well on a 17025 criteria. And I wish you all a great afternoon. Thank you.